Hello, everyone, and welcome to Lecture 17 of GPU Computing. Today, we're going to be talking about sparse matrix computation. We started this topic last time, and today we're going to be continuing to talk about it, and we're going to focus on new storage formats, particularly the ELL and the JDS format. So last time we started talking about sparse matrix computation, and there are many different kinds of sparse matrix computations. We were focusing on sparse matrix vector multiplication. And one of the important considerations that go into optimizing sparse matrix computations is the choice of the storage format. A lot of times, the storage format that we use to store the matrix, the sparse matrix, to some extent dictates the kinds of approaches that we can take to perform the sparse matrix computation. So we have been looking at, last time we looked at the COO and the CSR storage format, and we looked at them particularly in the context of SPMV, because different storage formats may be good for different computation. So we saw the COO and the CSR storage formats, and we looked at their advantages and disadvantages, and today we'll be talking about two new formats. So let me recap on what we did last time. Last time we looked at sparse matrices. We said dense matrix has all non-zero elements, or the majority of elements are non-zero, whereas a sparse matrix has the majority of elements are zeros, and we can take advantage of the fact that they're zeros by not storing them, which saves memory, and also not loading and computing with them, which saves memory bandwidth and computation time. And we said that we're going to look at several different storage formats. We looked at COO and CSR last time. We're going to look at ELL and JDS today. And we said that one of the design considerations that go into these storage formats is their space efficiency, how much they save space, the flexibility, how easy is it to modify the matrix by adding or reordering elements, their accessibility, whether they make easy to find, what information is easy to access using this format, what information is not easy to access, and then the memory access patterns. So do they enable coalescing? And this usually relates to a particular workload. So we're looking at SPMV. So we've been looking at which formats enable coalescing specifically for SPMV. And the other is load balance. Do they help with load balance, or in the context of GPUs, do they minimize control divergence? And again, this has to be looked at in the context of a particular computation, and we're looking at it in the context of SPMV. So SPMV is where we take a sparse matrix and multiply it by a dense vector to obtain another dense vector. And this is the computation that has been guiding our study of the different sparse storage formats in last lecture and also today's lecture. So we started with a COO format, and we said that the COO format is a format where we simply store all the values and in one array, and we also store the row index and the column index at the corresponding location in two other arrays. So we have an array for the row indices, array for the column indices, and array for the values. And we said that if we want to perform SPMV using the COO format, the typical way of doing it is assigning a thread for every non-zero in the sparse matrix, which corresponds to assigning a thread for every location in these arrays. And that thread will be responsible for reading the value, reading the input at the column index, and then updating the output at the row index. So this is how we parallelized SPMV with the COO format. Another format was the CSR format, and the CSR format is basically where we do have the values in the columns, but they're grouped according to rows. And rather than having a row index, we just have rather than having the row indices, we actually have a row pointer, which is basically an index into these column and value arrays that tell us where the elements of a particular row start. So the advantage of CSR is that it allows us, given a row, finding all the non-zeros in that row, which we couldn't really do with CSC, so with COO. However, the disadvantage is that it becomes harder here to modify the matrix by adding new non-zeros, as opposed to COO, where adding new non-zeros is easy. You just append them at the end of the array. Also for SPMV, we saw how with CSR, we don't need to have the atomic operations because every thread owns an output element. We don't have multiple threads writing to the same output element. So we save on the atomic operations. However, we do incur the cost of having our uncoalesced accesses, because each thread is going through one of the rows, so the thread is not going to access the data in a coalesced way. And also we have control divergence, because each thread is going, different nodes have different numbers of non-zeros, so each thread might be going through a different number of non-zeros for the row that it is responsible for. So this was an overview of what we covered last time. And today what we're going to do is we're going to look at sparse matrix vector multiplication still, but we're going to look at different storage formats today. In particular, we're going to look at the Ellpack format, which is abbreviated as ELL, and the Jagged diagonal storage format, which is abbreviated as JDS. Before I begin, any questions about what we covered last time? What I would like to do before we begin, actually, is I would like to remind you of the performance that we got last time. So this was the COO implementation we had last time, and this was the kernel time we got. And then we also had the CSR implementation, and this is the kernel time that we got for the CSR implementation. So it turned out actually that it was worth doing the atomic operations to get code. We saw that with CSR gave us more control divergence and poor coalescing. COO gave us better coalescing. However, and better control divergence, but the price was the atomic operations we had to do. And for this particular matrix, COO happened to be better. For other matrices, it might be the case that CSR is better. Okay, so just keep these numbers in mind, because we'll refer to them later on when we go to implement another SPMV kernel based on a different format. So what we'll start with today is we'll start talking about the Ellpack format. So the Ellpack format is as follows. If I have a matrix, okay, this matrix over here, what we are going to do is similar to CSR. We are going to group the non-zeros of each row together. Okay, so here we're going to have the column indices and the values of the non-zeros, and we're going to group them together like this. So we're going to have the non-zeros of the first row, followed by the non-zeros of the second row, followed by the non-zeros of the third row, followed by the non-zeros of the fourth row. Okay. However, we're not just going to put them all in an array like this. What we will do is we're going to pad each row. We're going to pad each row so that the rows all have the same size. And what I mean by pad is that we're going to put these kind of elements that don't really, we're going to have in memory, we're going to have these elements that are not really useful. So they're going to take up some space, but they're not going to be useful. However, what they do is they help me make this array that's storing these non-zeros a little bit more regular. Okay, because now each row is going to have a fixed amount of memory dedicated for it. Okay, so as you can see, this is probably going to help us with coalescing later on. Now, after we do this, what we're going to do, so after we add these padded elements for each row, such that all the rows have the same number of elements, even though some of these elements are not useful elements. Okay, what we're going to do is we're going to store the padded array of non-zeros in column major order. Okay, so instead of storing these non-zeros, 1, then 7, then this padded element, then 5, then 3, then 9, then 2, then 8, then the padded element, rather than going in row major order, we're actually going to store these in column major order. So we're going to store the 1, and then the 5, and then the 2, then the 6, then the 7, then the 3, then the 8, then the padded element, then the pad element, then 9, the pad element, the pad element. So what's happening here is we're actually taking the first element of each row and we're putting them next to each other in memory. Then we're taking the second element of each row and we're putting them next to the second element of each row and we're putting them next to each other in memory. Then the third element of each row, etc. So if we flatten this array, so if we look at what this looks like when we flatten it, it's going to look like this. Okay, so here I'm going to have the first element of each row, and then the second element of each row, and then the third element of each row, etc. Okay, is this clear?
Professor, if we have an empty row, then we pad zeros on the whole row.
Right, exactly. If you have an empty row, then so if we go back, If you have an empty row, then just all of these will be padding.
Okay, thank you.
Okay. Okay, so now let's say we want to implement SPMV using this ELL format. Okay, so let's say we want to take this matrix, multiply it by a vector to an input vector to get a corresponding output vector. How can we parallelize this? Well, we're going to use the same approach that we used with CSR. Okay, we're going to assign a thread to every row and its corresponding output element. And that thread is going to go through the non-zeros of that row, okay, and compute the output element. So we're going to assign one thread to loop over each input row sequentially and update the corresponding output element. Okay, so here every thread is responsible for the row, and every thread starts with the first non-zero element in that row. If we look at what that looks like in terms of accessing the value and the column arrays, every thread is going to start with the first element in the row. And what you notice here, you notice that the memory accesses are coalesced. And then the threads together move on to the next element in their row. So each thread goes to the second element in the row. You know what, this thread is done, so it's going to hit a padding element. And it's basically, so there's two ways of dealing with this padding element. Either we don't do anything, or we put a 0 here so that we do actually compute something, but the value is going to be 0. So we're going to multiply and add a 0, so it's just not going to have any effect. Okay, and then we move on to the third element of each row. So now we have this one more thread still has the work to do, but the other threads are just going to hit the padded elements, and then we're done. Okay, is it clear? Any questions? Okay, well then let's go and implement this and see the performance that we get. So I'm gonna switch the code over here. I'm going to go to my ELL implementation. Okay, and here, as you can see, I've already written the code for allocating the matrix and copying it and calling the kernel, etc. Let me just give you a glimpse at what the ELL data structure looks like. Here in the ELL data structure, we're going to have the number of rows, the number of columns, naturally. We're going to have the maximum number of non-zeros per row. The maximum number of non-zeros per row is basically going to tell us how many times we need to iterate through this array. Okay.
Professor?
Yes?
Just one small question. Getting the array into this format, isn't it very expensive?
So yes, that's a good observation. So if you want to convert the array to use this format, there's some conversion cost. Okay. However, usually a lot of times when you use sparse matrices in actual computation, you might use a sparse matrix many times, right? So I might not just be multiplying the matrix by one vector. Maybe I'm iteratively multiplying it by vector over and over again. So if I'm going to use the matrix 1,000 times, if I'm going to do 1,000 matrix vector multiplications, you know, or maybe even more, it becomes worth to convert the matrix into a useful format so that you can save performance on each one of those SPMV operations. But if you're going to do the SPMV only once, then yes, maybe it's not worth incurring the conversion cost to optimize only one SPMV operation. Okay, that's a very good observation.
Okay, thank you.
So the maximum number of non-zeros per row tells us basically the maximum number of non-zeros per row, and that helps us know if we go back, this helps us know the dimension of this 2D array that we're flattening. The maximum number of non-zeros per row is going to be the width of this over here. Okay. Okay, and then we're also going to have the number of non-zeros in each row. So the number of non-zeros in each row allows me to know when to stop. So here, how do I know that this thread is not supposed to do anything for this element? Because I'm going to track the number of non-zeros, the actual number of non-zeros in each of the rows, right? So even though I have a padding element, maybe I don't want to load and compute with the 0. Okay, and then finally, of course, I need to have the column indices and the values, which are these two arrays. Okay, so given this information, how do I implement the ELL kernel? Well, let's start first of all by assigning each thread to what it is responsible for. Okay, if each thread is going to be responsible for a row, okay, so basically I'm going to use the thread index in order for me to determine what row the thread is responsible for. So I will write unsigned int row is equal to block index.x times block dim.x plus thread index.x. Okay. Then I have to do a boundary check to make sure that the threads in the last thread block are not doing anything out of bounds. So I'm going to check if my row is less than the num rows over here. Okay, so I'm going to do ELL matrix dot num rows. Okay, now after I do the boundary check, next what I would like to do is I would like to have the threads loop over their non-zeros. Okay, I want to have the threads loop over their non-zeros. How do I have the threads loop over their non-zeros? Well, I'm going to have a loop. Okay, unsigned int. I'm going to name the loop bound maybe the iteration, right? Because all the threads are going to iterate through their non-zeros. Okay. Equals 0. The iteration is less than, and then I have two approaches that I can take here. The first approach is to have all the threads iterate through all the non-zero elements, including the padding, load the padded element, which would be a 0, and then multiply and store. Okay, it's not going to affect the computation, but I would waste a load in this case. I would waste the time loading. So I could do go until iteration is less than maximum number of non-zeros per row, and load and compute with the padding elements, and it won't have an effect on my computation. But that tends to be wasteful. So another approach is to have every thread stop when each thread has reached the number of non-zeros in the row that it owns. And this is where it's useful to track this NNZ per row. So this NNZ per row is not necessary, but it's an optimization for me to avoid having to compute the padding element. So here, rather than having this blue thread, compute this padding element, so multiply and add the 0, I can simply remember the number of non-zeros in the second row that it's 2 to completely deactivate this thread when I reach this iteration. Okay, so either approach is fine. The approach that I'm going to use is to track the number of non-zeros per row so that I don't have to load and compute with the padding elements unnecessarily. Okay, somebody's saying this is causing control divergence. Well, yes, it causes control divergence, right? But if you're gonna pad, okay, and you're multiplied by 0, you're not gonna have control divergence, but the work that you're gonna do is going to be useless. Okay, so it's as good as having control divergence. Okay. So what I will do is I'm going to check that iteration is less than ELL matrix dot the number of non-zeros per row of the row. Okay, and then I'm going to increment the iteration. Okay, so now in this loop, what I would like to do is I would like to now find the index of the non-zero in the value and the column array. Okay, so what's the index going to be? Well, let's go back and take a look at the. Let's go back and take a look at this. So if the iteration is going to be the horizontal index for this array, okay, and the row is going to be the vertical index for this array, and this array is stored in column major order, okay. So basically, the index into this array of my non-zero element is going to be the iteration times the number of rows plus the row index. Okay, is that clear? It's the iteration times the number of rows plus the row index. And if you want to go back and see it on the in this actual array, what we're doing is we're saying the iteration. So if I'm in the first iteration, I'm going to be processing these elements. Second iteration, I'm going to be processing these elements. Third iteration, I'm going to be processing these elements. So when I take the iteration and I multiply by the number of rows, it takes me to the chunk of elements that I'm processing on this iteration. Okay, so iteration 0, I'm here. And iteration 1, I'm going to go to 1 times the number of rows, which brings me here. Iteration 2, I'm going to go to 2 times the number of rows, which brings me here. And then plus, I'm going to add the row index. Okay, so if I'm on iteration 1, I'm going to do 1 times the number of rows, which brings me here. And then I'm going to do plus the row index. So if I'm row 0, I'll be here. If I'm row 1, I'm going to add 1, I'll be here. If I'm row 2, I'm going to add 2, and I'll be here. Okay, so the index into this array, I'm going to call it I, is going to be equal to the iteration times the number of rows. Okay, we can get that from the matrix. Okay, plus the index of the row itself. Okay, now that I've done this, I have the index into this array of the for the non-zero element that I care about. So I'm going to load its value and I'm going to load its column index. Okay, so I'm going to write unsigned int column is equal to ELL matrix dot column indices of I and float value is equal to ELL matrix dot values of I. Clear? Is it clear how I found where the non-zeros are in this array? And as you can tell, it's clear here why there's coalescing, because I is expressed in terms of row, and row is expressed in terms of thread index dot x. So threads with consecutive thread index dot x values are going to have consecutive row values, and threads with consecutive row values are going to have consecutive I values, and therefore threads, when the threads load from the column indexed array, consecutive threads are going to have consecutive I values, so they will load consecutive elements from the column indexed array and from the values array. Okay, now that I have the column index and the value, the rest is easy. We've done it before. We simply out vector of row plus equals in vector of column times the value. Okay, so we obtain the for each thread we obtain the non-zero that it needs, and then the column index that it is, and then based on its column index we load the corresponding element from the input vector. We multiply that element with the non-zero, and we store that result. We accumulate that result to the output vector. Okay. And of course, since to avoid having to go to global memory every time, what we can do is we can simply create an accumulator at the beginning. So float sum is equal to 0, and then here we can accumulate to the sum variable. And down here we can write out vector of row is equal to sum. Right? Is this clear to everyone? Any questions about this implementation?
Professor, the padding is not so much for the, like, avoiding control divergence. It's just to have the fixed array size to be able to know for sure, like, the dimensions.
The padding, yes. So the objective of the padding is what allows us to do this.
Yeah, okay, I see. So to have a modular.
Yeah. If this
okay.
wasn't padded, then I'm going to, then my I can't just calculate the I based on the iteration and the number of rows and the row. Okay,
Right,
I would have to load, just like we did with CSR. With CSR we had to load a source pointer that told us where the row starts, and then everything was next to each other. The reason I every thread skip a constant number of elements every time to get my next value, okay, is because I have this padding.
Okay, thank you.
Okay. If I didn't have this padding, then I'm going to have to do all kinds of things to figure out which you know what element the thread is responsible for. Okay, well, let's compile this and run it. Okay, so I'm going to compile and I'm going to run. Okay, and as you can see, we indeed do get better performance than the CSR version. Why? Because compared to the CSR version, we have better coalescing and we have, well, not necessarily less control divergence, but we do have better memory coalescing. Okay?
But the
So
copy
ELL
time is
compared to
huge.
CSR reduces control divergence. It reduces memory coalescing. Yes?
Sorry for interrupting. I said that the copy time is huge. Is it because of the padding?
Right, so very good observation. So the copy time is much larger compared to CSR. Why is the copy time much larger? You're absolutely right. It's because of padding. So copy time is related to space efficiency, right? And since the ELL format has all this padding, it's going to take up much more space, and that is why the copy time is much larger. So that's a very good observation. Okay, so let's go back to our different performance, different factors that we talked about that go into designing the storage format. Okay, we said that we have several considerations. One of them is space efficiency. How does ELL compare to CSR in terms of space efficiency? Well, we just observed that the copy time is much larger. It's going to be less space efficient because of all the padding, right? So ELL is less space efficient than CSR. What about the flexibility of adding and removing values? How does ELL compare to CSR in terms of that flexibility?
You need to add padding or stuff like that to add a new value.
Well, let's take a look. If I go back, yeah, I can just do it here. So let's say I wanted to add a new non-zero to the blue row, the first row. Is that easy or hard to do?
As long
Yeah.
as you're not on the maximum row, you can just add it where there's padding.
Right, exactly. So here, because this first row does not use all of its values, there's this padding value that we're not using. We can actually use this padded element if we want to add a row in the future, add a non-zero in the future. So in this example, the only row we cannot add a non-zero to is the second row because it already uses all the elements. But for all the other rows, because they have padding, we can if we want to add a non-zero, we can replace the non-zero with the padding. And because the way we run our kernel kind of takes into consideration the fact that there might be padding, if we want to remove an element, we can remove it and replace it with padding.
But Professor, shouldn't the second row have 4 elements? 3 are normal and 1 padding element?
No, because remember, if we want to have 4 elements, what that means is that we're going to allocate as much memory as this matrix needs. So that beats the whole point of using a sparse representation. Okay, so the amount of memory we're going to allocate for the ELL is going to be just enough for us to be able to store the maximum, the row with the maximum number of non-zeros. Now, in this illustration, it's 3 out of 4, but in practice, the row with the maximum number of non-zeros is going to have much fewer non-zeros than the width of the matrix. Okay. Okay, so then in terms of space efficiency, ELL is worse than CSR. In terms of flexibility, ELL is better than CSR. It's easier for us to add elements and remove elements, except for the last the row with the largest number of non-zeros. For that row, we're going to have it's going to be more we can't add non-zeros to that row. Okay, without of course making major changes to the whole data structure. So what about accessibility? What does ELL make it easy to access and hard to access? So remember, with COO, given a non-zero, it was easy to find the row index and the column index. With CSR, given a row, it was easy to find the non-zeros for that row. What about ELL? So with ELL, given a row, can we find the non-zeros of that row? Well, yes, we can, right? Because we can just stride over the number of rows every time to find the next non-zero for the row. Okay. And this is obvious. This would be obvious in the code because we just had the number of non-zeros and the index of non-zero that we want, and we're able to find where that non-zero is. So given a row, it's easy to find the non-zeros in that row in ELL. What about the other thing that we want with COO? Given a non-zero, is it easy to find the row and the column for that non-zero?
Yes.
Yes.
Well, it's easy to find the column, right? What about the row? How can we easily find the row?
Using the stride.
We take modulo.
Right. Right,
max
exactly.
size.
We just do modulo the number of rows. Okay, if we do modulo the number of rows, we can find the row. Okay, and this is clear if we go back and look at the code. When we calculated the non-zero and the index of the non-zero, the way we did it is we did iteration times number of rows plus row. So if we have the index of the non-zero and we want to find the row, we can simply do modulo the number of rows, and we can find our row. So ELL actually gives us, in terms of accessibility, ELL gives us what both CSR and COO give us. Given a non-zero, we can find the row and the column index, and given a row index, we can find the non-zeros in that row. And in fact, if we wanted, we could have done a non-zero based parallelization for ELL. We could have assigned a thread to every non-zero, okay, and then had the thread atomically update the output. I'm not going to implement that, but hypothetically we could do that. Okay, so in terms of accessibility, ELL gives us more accessibility than COO and CSR. What ELL doesn't allow us to do is, given a column index, find the non-zeros in that column. We cannot do that with ELL. However, just like there's CSR and there is CSC. Remember how we had CSR compressed sparse row, and we had compressed sparse column, which was like CSR, but made it easy to access the columns. We can do the same thing for ELL. We can have the kind of the transpose of ELL, where you would make it easy to access the elements of the same column, but then you cannot access the elements of the same row. So we can have kind of a different version of ELL for doing a column-wide traversal, just like we have the CSC alternative to CSR for doing a column-wide traversal. Okay, what about memory coalescing? Well, that was the whole point, right? The whole point of designing ELL is so that we can improve on the memory coalescing. So ELL is better than CSR in that it gives us memory coalescing. And in contrast, it's better than COO because it allows us to access the output as well in a coalesced way, as opposed to doing all these atomic operations to update the output. Okay, and then finally, we have control divergence. So how does ELL compare to CSR in terms of control divergence?
It has less.
How so?
Isn't CSR the one where we had a lot of control divergence?
Well, the reason we have control divergence in CSR is because every thread processes a different row. So each thread is, because different rows have different numbers of non-zeros, each thread will have a different number of loop iterations, and that's where the control divergence comes from. Have we changed anything about that when we moved to ELL?
Haven't we introduced zeros into the the numbers, the padded numbers, I guess. How do we call them?
So we added these padding elements, right? Okay, but if we go back and look at the code, okay, we're still iterating for each row. We're still iterating according to the number of non-zeros in that row. Okay, so in CSR, every thread looped over the non-zeros in that row, in its row, and in ELL, also every thread is looping over the non-zeros in its row. Now, again, if rather than doing this, we actually every thread looped over the max, and we process the padding elements, even though the threads are not going to diverge, they're going to be doing useless work. So practically, it's as good as having control divergence. In fact, it might be even worse because you could have a warp where all the threads are done, and all the threads would go and process padding elements. So this is actually a better approach in terms of control divergence. Okay, so ELL doesn't really solve the control divergence problem, but compared to CSR, what it does solve is the memory coalescing problem in CSR, and at the same time, it solves the problem with the atomic operations in COO. Okay.
Professor,
Yes.
since we're like taking every row and putting the elements, all of them, at the left first, and then like taking the column major order, so isn't it like more likely that we have more actual elements than padding on the left and more padding than actual elements on the right? So then maybe a control divergence is a little bit better because we're more likely to have warps of the same, like doing the same thing, either completely active or completely inactive.
But that's the same thing with CSR, right? So we haven't really changed the amount of work that each thread is doing when we go from ELL to CSR, right? It's true that the non-zeros are going to be to the left and the padding is going to be to the right. But in CSR, for the initial iterations, the threads are more likely to have non-zeros, and for the last iterations, the threads are more likely to have completed going through the non-zeros in their list. Okay, so we haven't really changed anything about that, right? Every thread is still doing the same amount of work that it was doing when we were using CSR, which is it's looping through all the non-zeros in the row that it owns. Okay, is that clear?
Yes, thank you.
Professor?
Yes.
Is so is the worst case of ELL is, for example, when one of the rows has kind of a lot more elements than all the others?
Yes, great question. I'm about to talk about that. So great question. Hold on to that, and I will talk about that very shortly. So this is the code that we wrote, and summarize, these are the trade-offs that we talked about. We said the advantages are that it gives us flexibility. We can add new elements as long as the row is not full. In terms of accessibility, it's better than both CSR and COO because we can, given a row, find the non-zeros, but also given a non-zero, find the row in the column, which is what CSR and COO both allow me to do. For memory coalescing, implementing SPMV using ELL enables coalesced memory access. On the other hand, the disadvantages are space efficiency. So we have a lot of overhead due to the padding, and we saw how much the copy time took compared to the others. Also, accessibility. So given a column, we cannot find all the non-zeros, but COO and ELL also did not allow me to do this. Only CSC allowed me to do this. And then finally, control divergence. So SPMV ELL has control divergence. Now, one of you said that in ELL, well, one of the problems with ELL is we could get into the situation where we have one row that has a very large number of non-zeros, and what that row will do is it will kind of hold all the other rows hostage because we're going to have a lot of padding just to accommodate that row. So let me show you an example of that. Actually, the slide title kind of gives away what we're going to do. We're going to do a hybrid ELL and COO. Let me motivate why. So if we have a matrix like this, where each row has like one or two non-zeros, but I have a very small number of rows that have many non-zeros. Okay, when I convert it to ELL, it's going to look like this. What you'll notice here is that most of these rows have a lot of padding. There's only 2 rows, the second row over here and then the second to last row down here. These rows use most of their elements, but the remaining rows have a lot of non-zeros. And what that means is I'm going to have a lot of padding that gets wasted. Now, what we can do to overcome this problem is rather than using ELL, we can use a hybrid between ELL and COO. What we can do is we can find kind of some number where most of these rows are below that number and use that as the width of our ELL representation. And for the rows that exceed that number, we can put the remaining non-zeros in COO. So for example, here I observe that most of my rows have less than 2 elements. So what I will do is I will have an ELL representation of the first 2 elements of each row. Okay. And this helps me capture all the rows in ELL except for 2 of the rows. So for these 2 remaining rows, what I will do is I will represent their non-zeros using COO. Okay, and then in this case, I can do an ELL implementation for most of the rows, and then I would have a COO STMV implementation to update the remaining the rows that have an excessive number of elements. And this allows me to have kind of the benefit from ELL, but at the same time mitigate the problem of padding. Okay. So ELL plus COO is similar to ELL, okay, but with the following benefits from using COO, we have better space efficiency because we have less padding, and also now we have more flexibility because if we go back, before with ELL, if we want to add it, we can add an element to these other rows, but if we want to add an element to the second row, we cannot because we've reached the maximum. There are no padding elements that we replace. But with hybrid ELL COO, if we want to add an element to a row, no problem. We can add an element to any row by simply adding it, by checking if there's a padding, and if there's no padding element for us to replace with a non-zero, we can simply go and add it to the COO part of the representation. Okay? ELL plus the hybrid ELL COO gives us all the benefits of ELL, but add to that the fact that we have less padding, and we also have the flexibility of adding element to any row as opposed to just the rows that have it maxed out. Is that clear? Any questions?
Professor, couldn't we have cut the long rows and added them as a new row, like cutting it in 2 and adding a new row, because we can just expand and we can combine them later on when like we have the kind of like partial sums in the output vector, and then we combine them.
But remember, if you make them a new row, but these 2 partial rows need to update the same output element.
Yeah, but no, I mean we have them update 2 different elements that we combine only at a later stage.
Okay, but then what you're going to have to do is you're going to have to do some operation where you start figuring out what elements need to be combined and what elements do not need to be combined, and combining them, and then moving the data, reshuffling the data so that you combine the elements and remove the excess elements, and that might be even more expensive than just doing it this way. But there is the approach of taking a row and breaking it down and doing different parts of it in parallel and then directly updating the output element. That approach is possible, and there are approaches like that try to optimize control divergence like that, where they break a single row into multiple rows. So hybrid ELL COO is one way to deal with long rows. Another way is, like you said, to partition long rows and have multiple threads work on them. But typically, we wouldn't do it by making them, logically 2 different rows. It would stay 1 row. It would still update the same output element, output vector element. But you'd have to have some kind of additional bookkeeping in your storage format to keep track of the fact that these different partitions of the row being passed by different threads belong to the same row.
Actually, Professor, wouldn't it lead you to doing something very similar to ELL plus COO? You would have another matrix or
not really. So here with ELL plus COO, we're going to have 1 thread that's going to go through these elements that are in the ELL part, and then we're going to have different threads process each of the elements of the COO part. Okay, whereas if I take this row and I break it in two, I would just have two threads. One thread does the first half, the other thread does the other half. Okay, so it's slightly different than so partitioning a row is slightly different from having a partial ELL row and then the rest of the elements in COO. Because COO doesn't have the concept of elements of the same row anymore. These elements could be in any order here in this array.
Okay, I see. Thank you.
Yeah, you're welcome. Yeah, all these are good questions. And you know, all these ideas that you guys are kind of proposing are definitely things that people always, you know, try to people, you know, come up with, and they try to apply these ideas to further and further improve these storage formats. And again, different storage formats are good for different computations. So sometimes some storage formats might be good for some computation, but not another computation. Okay. Okay. So what is our problem still? So we with the ELL format, we solved the coalescing problem, but we still had one problem, which was what? So both CSR and ELL still had this problem.
It's not
Having
easy.
So ELL was better than CSR in that it reduced, it improved the coalescing behavior, right? But ELL and CSR both still have a problem, which is what? That makes them inefficient? Control divergence, right? So somebody wrote control divergence. So to address the problem of control divergence, there's another storage format that optimizes for control divergence, and that's called the Jagged diagonal storage format, or the JDS format. And the JDS format works like this. If I have this matrix over here, what I'm going to do is similar to what I did with CSR. I'm going to group non-zeros together. So the non-zeros of the row are all kind of grouped together. By the way, here when I say grouped together, I don't mean physically grouped together. I mean logically. I'm going to think of them as kind of one thing. Okay. Now, if you remember, the problem with CSR and with ELL is that different threads were processing different rows, and threads that were next to each other could be assigned to rows that have a significantly different number of non-zeros. So your thread 0, the row that thread 0 is responsible for has 1 non-zero. The row that thread 1 is responsible for has 4 non-zeros. They have a significantly different number of non-zeros. So what can I do? So the main problem with control divergence is when threads that are next to each other are processing rows that have a significantly different number of non-zeros. So what can we do to avoid this? What can we do to have threads that are next to each other process rows that are of similar size so that we have less control divergence?
Sort by row size, reorder.
Right, exactly. So what the JDS format does to reduce control divergence is that it sorts the rows by the size of the row. So the green row will go first, and then these two rows with 3 elements, then the rows with 2 elements, and then the rows with 1 element. So we're going to sort the rows. Okay, but of course, we still need to know what element to write to, right? So we still need to know what is the original row index. So we will have another array that keeps track of the original row index. So this array tells me that the row that is now in position 0 is actually row number 1. The row that is now in position 1 is actually row number 3. The row that is now in position 2 is actually row number 5. The row that is now in position 6 is actually row number 0. Okay. So we will sort the rows like this. And then next what we will do is, so sorting helped me solve the problem of control divergence. But I also want to have good memory coalescing. So what can I do to have good memory coalescing? Well, I want, when my threads come to access the first element of their row, I want the accesses to be coalesced. Okay, so when thread 0 comes to access this non-zero element, and thread 1 comes to access this non-zero element, and thread 2 comes to access this non-zero element, etc., I want my accesses to be coalesced. So what can I do to make those accesses coalesce?
At store time, the threads become responsible of the unsorted version.
Nope. I'm going to sort these physically. Okay, I'm not talking about storing to the output element. I'm talking about when they want to read to the actual non-zeros in the matrix.
Oh, they can read the unsorted version and place it in the sorted. Oh no, that doesn't make sense.
So if I want the thread 0 when thread 0 accesses this element, and thread 1 accesses this element, and thread 2 accesses this element, I want the access to be coalesced. Well, what that means is I want these elements to be stored next to each other. Okay, so rather than what we did in CSR, where we stored the non-zeros of a row next to each other, and then the non-zeros of this row, the non-zeros of this row, what we can do is we can store the non-zeros across the column in this array. Okay, so we're going to store the non-zeros in this order. Okay, kind of column wide, and what that results in is an array that looks like this. Okay, I have all the first non-zeros of the first row, and what taking into consideration sorting, and all the second non-zeros of the second row, and all the third non-zeros. Sorry, all the third non-zero of all the rows, and then all the fourth non-zero of all the rows. Okay. This is similar to ELL, but without the padding and with the rows being sorted. Now, the problem here is that when the thread now wants to loop over the non-zeros that it owns, how does it find them? So here, thread 0 is going to be responsible for the largest row, which is this green row over here. So it's going to start at this element here. And then to get to the next element in its row, it needs to jump 6 by a stride of 6. But on the next iteration, it's going to jump 5 elements. On the next iteration, it's going to jump 3 elements. Okay, so how does a thread know how many elements it needs to jump? Well, what we are going to need to do is we're going to have some kind of array to tell us where the beginning of the non-zeros for each iteration. And I'm going to call this the iteration pointer. It has many different names. I'm going to call it the iteration pointer array. So 0 tells us that the first non-zero of each row, or the non-zeros that are the first in their row, are going to start at index 0 in these two arrays. The non-zero that's second, the non-zeros that are second in their rows are going to start at index 6. The non-zeros that are third in their rows are going to start at index 11, etc. Is this clear so far? Okay, so now let's see what happens. Now what we will do is we're going to assign a thread to every row. So now that we want to do SPMV, we're going to assign a thread to every row. Okay, and in terms of the access pattern, that looks like this. So here I'm going to have a thread responsible for every row. So thread 0 is responsible for the first element, this row over here, and I know that this is row 1 because by looking at this permutation vector here. So thread 0 is going to be responsible for row 1. Thread 1 is going to be responsible for row 3. Thread 2 is going to be responsible for row 5, right, etc. And now each thread is going to load the first non-zero of the row that it's responsible for. And as you can see, these memory accesses are coalesced. Now on the second iteration, what happens? In the second iteration, the threads are going to start from index 6. So they're all going to come here. Okay. And all of them are going to load except the threads that are done. So here, this blue thread here is done because it has no more non-zeros in its row. And because this is the smallest row, this blue thread that drops out is going to be the last row in the sorted array. So it's going to be the last thread. Okay, so the thread that drops out, it drops out from the end. The thread that drops out is the last thread. And because the thread that drops out is the last thread, not, I don't have arbitrary threads in the middle dropping out, they're dropping out from the end. This is what minimizes control divergence. Okay, and I can do the same thing when I move on to the next iteration. The threads will go, they'll look, by the way, the way for me to know which thread drops out is I can simply look at the next iteration pointer. Okay, so the threads that should compute are the ones starting at 6, and then anything that's above 11 should not be computed. So here, this blue thread should not compute because this element is not a blue element. The blue elements are done. This element is actually for the next iteration. Okay, on the next iteration, we have more threads are complete. So these 2 threads that correspond to the rows with 2 elements are done. Okay, so but again, these threads are going to drop out from the end because these 2 rows that have 2 elements, these are the last 2 rows after we do the sorting. Okay, so now the last three threads are dropped out. The first 3 threads are still active, and each thread loads the non-zeros that it's responsible for in a coalesced way. And then on the last iteration, most of my threads are done. I only have 1 thread left that is still computing for the largest row, and that thread does the computation while all the other threads have dropped out. Okay, and in practice, these threads could spend many, many warps. Okay, so if every 2 threads here are a warp, and then on this iteration, I already have 2 warps that are gone and only 1 warp is active. Okay, in practice, warps are 32 threads, not 2 threads, but I'm just giving a kind of an example. Okay, is this clear? Any questions about this? Okay, so let's talk about the different advantages and disadvantages of the JDS format. First, in terms of space efficiency, how does the JDS format compare to ELL, for example?
It's
more space efficient.
Right, exactly. So JDS is more space efficient because there isn't any padding. It's not as space efficient as CSR because we have additional things we have to keep track of, right? We have the column, we have the value, but we also have the iteration pointer. We have this permutation vector that we need to remember. So we have more bookkeeping data that we need to keep around. So it's not going to be as space efficient as CSR, but it's going to be more space efficient than ELL because there's no padding. What about flexibility? So ease of adding and removing elements from the format.
It's terrible.
Right, exactly. It's very hard to add and remove things here. Okay, maybe even harder than CSR, because when you add, you might change what row is larger and what row is smaller, and that makes things really difficult. Okay, or even when you remove, you've changed what rows are larger and smaller. Okay, so JDS does not give us flexibility when it comes to adding and removing or modifying the matrix in general. What about accessibility? So like CSR, with JDS, given a row, it's easy to find all the non-zeros in that row. Okay, well, not necessarily given a row, but given kind of an index, right? But if I want to find row 1, I would have to actually search this array to find row 1 corresponds to where in the new sorted order in order for me to actually find row 1. So it's actually more difficult than CSR to just given a row find the non-zeros. What you could do is you could have an inverse of this vector. So where here this vector given kind of the new row index, it gives you the old index. You could have another vector where given the old index, it gives you the new index. Okay, so given the original order, it gives you the sorted order. This one, given the sorted order, it gives you the original order. Okay, so JDS, in terms of accessibility, it's slightly worse than CSR, but with a little bit of work, given a row index, we can find the non-zeros of that row. What about given a non-zero? Is it easy to find the row index and the column index? It's easy to find the column index, but it's quite difficult to find the row index. Okay. And then given the column index, you almost cannot find anything with JDS. Of course, I mean when I say you can't find anything, I mean you can't find anything easily, right? If you want to do some expensive searching, you can eventually find what you want, but you can't do it easily. Okay, so that's space efficiency, flexibility, and accessibility. What about coalescing?
It's very coalesced.
Right, the coalescing is good because we have the arrays are the axes are sorted. Sorry, the rows are sorted. It's actually even better than ELL, right? Because if we go back and if you remember with ELL, when we are doing the coalesced axes, right, at some point we reach a point where we have these padding elements inside of our axes. So even though our axes are coalesced, some of the values that are in that coalesced axis are actually not used. Whereas with JDS, we're gonna have coalesced axes, but we're also gonna fully utilize the coalesced memory request. Okay, so it's even better than ELL when it comes to coalescing. At least it's the same when it comes to coalescing, but we have fewer memory requests because we're fully utilizing memory requests. And what about control divergence?
It's good.
Right, the control divergence is also very good because because the control divergence is also very good. And that was the whole point of doing JDS. Because we sort the rows, the control divergence is quite good. Okay, so these are the trade-offs of JDS. The advantages are space efficiency. We have no padding. Accessibility, given a row, we can find all the non-zeros. The memory axes are coalesced, and it minimizes control divergence. But the disadvantages are that it's hard to add new elements to the matrix, and given a non-zero, it's hard to find a row, and given a column, it's hard to find all the non-zeros. Okay, I'm not going to implement JDS with you because I want to keep that for you as an exercise to do on your own. But what I will do is I will run it for you so that you can compare its performance to the other implementations. So here, I'm going to compile the JDS kernel, and I'm going to run it. Okay, and as you can tell, the JDS kernel performs better than the ELL kernel, and it also performs better than the CSR kernel. And let me zoom out a little. It also performs better than the COO kernel. So the JDS kernel actually has the best performance between all the kernels that we implement. All right. Also, one thing to note here, although COO is doing pretty well because it reduces the coalescing. So it has better coalescing and control divergence than CSR and better control divergence than ELL. Okay. In practice, COO may not be as good if we go for other matrices, especially when these matrices get much larger, because then we start having a lot of atomic operations, and they start to hurt our performance. But yeah, for the matrix that I'm using, it turns out that COO actually does pretty well when you compare it with CSR and with ELL. But of course, JDS remains to be the best performing kernel. Okay. Any questions?
Is this only in the case of SPMV, or does it change with other problems depending on like the requirements?
Excellent question. So yes, everything we're talking about when we talk about the trade-offs of the different storage formats is specific to SPMV. When we go to different computations, how we access the matrix for a different computation might be different. Okay, and in this case, JDS may or may not be the best format. All right, it's about how we access. It's also about how we parallelize. Okay, so all kinds of things again go into consideration when we change what the computation we're doing is. So for another computation, it may not be the case that this is how they will perform.
Yeah.
Relative.
Doctor,
Yes.
can you repeat how we reason about the accessibility for JDS?
Yes. So what I'm saying for JDS is that So for JDS, we can go through the non-zeros of a row quite easily. Okay, if I want the of the new row, the row after we sort. If I want to go through row 0 of the in the sorting order, which is row 1 in the unsorted order, I would just iterate through my iteration pointers and go to the go from the iteration point an offset of 0. If I want to go through row 1 in the sorted order, which is row 3 in the unsorted order, I would just go to the iteration pointer and add 1, and I find the corresponding non-zero. So in JDS, I can easily loop through the non-zeros of a particular row. Is that clear?
Yes, this part's clear.
Okay. Did I answer your question?
Yeah, but I wanted to know if given the column, why can't we find the non-zero element?
So given if I tell you go and find me all the non-zeros in column 2, how would you do it?
Yeah, I can't really think of a way.
Yeah, right. So you don't really have a way to do a column-wide traversal. In the same way that in CSR you can't do it, right? Given a column 2, you wouldn't be able to just go and find all the non-zeros in column 2 easily. Okay?
Okay, thank you.
Yeah, you're welcome. So then these are the trade-offs of the JDS format, and this concludes our 2 lectures on sparse computation and sparse matrix vector multiplication. And you can read more about what we talked about today in the remaining sections of chapter 10. Right? Does anybody have any final questions about sparse computations before we conclude? Okay, if not, then that's all for today, and I'll see you next time. Bye, everyone.